Hello, welcome everyone. Today we are going to study energy. So, in common language, we often use the word energy in different way. For example, a person is full of energy. When I tell a person is full of energy, a person is full of energy. Okay? Or a person is very lazy. Or a person is very lazy and has no energy and has what? No energy. Or this food is very energetic. Or this food is very energetic. We often use have we ever seen energy? Question is that have we ever seen energy? The answer is no. What we observe in our daily life is not the energy but the effect of what? Energy. In science, we give definite and proper meaning of energy. Now I am going to discuss certain situation, and those situations are suppose when we just touch the hammer on the nail to drive it into a wooden piece, no work is done. But if we raise the hammer vertically up and above the head of the nail, some work is done by us in raising the hammer. Again, if we allow it to fall on the head of the nail, it will do work in driving the nail into the wooden piece. Okay. Second situation is when a cricket ball just touches the stationary stump, nothing happens. But when the same cricket ball hits the same stationary stumps at fast speed, what happens? The wickets and stumps are thrown away, right? Other situations are when a child other situations are when a child winds a toy car and places it on floor. It starts moving, right? All of you have seen it. This is because there is a spring or a spiral shape inside the toy car. By winding the key, the child winds up the spring of the toy car and the spring gets coiled more tightly. The work done in winding the spring gets stored up in the tightly coiled spring. Okay? So when wound up spring gets released, suppose this is a spring, I am trying to draw it, and this we have tightened it. Okay, so this is normal shape, normal shape, and this one is wound up spring, and of course this pauses what? Energy. So when the wound up spring gets released to return to its original shape, it turns the wheels of the toy car and bring them in what? Motion. Thus we can say that a wound up spring can do the work by virtue of change of its shape. Okay, so from above analysis, bodies, any body acquire the capacity or ability of doing work through different means. In physics, the body having capacity to do work is said to possess energy, right? So energy of a body is defined as the capacity or ability of the body to do work. The amount of energy possessed by a body is equal to the amount of work it can do when its energy is released. One more important thing is that I would like to tell all of you about energy. More the amount of energy possessed by a body by a body, more the amount of work it can do it can do, and vice versa. Energy is a scalar quantity. Energy is a scalar quantity having no direction in space. A scalar quantity. Okay. Units of energy. So as far as units of energy is concerned, as we know that energy possessed by a body is measured in terms of ability of body to do work. Therefore, the SI unit of energy is the same as the unit of work. So it will be what? Joule. And 1 joule, 1 joule is the energy required or consumed to do 1 joule of work. 1 joule of what? Work. Larger unit of, this is one thing, this is second thing, larger unit of energy is kilojoule. Okay, and 1 kilojoule, 1 kilojoule is equal to 1000 joule. Okay, a smaller unit of energy is a smaller unit of energy is EV, electron volt. Electron volt, and 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. And as far as CGS unit, CGS unit, CGS unit of energy is erg, ERG, and 1 joule is equal to 10 raised to 7 erg. Okay, as far as forms of energy is concerned, forms of energy, forms of energy. So there are so many forms of energy: mechanical energy, mechanical energy, and it includes kinetic energy, plus potential energy. Okay, heat energy. Heat can be defined as the form of energy that is transferred between 2 points due to the presence of a temperature difference between the 2 points. When water boils, it changes to steam. The steam possesses heat energy because it has the ability to do work such as to run steam engines, turbine, etc. The heat produced by the burning of petrol in a car engine provides the energy needed to run the car. Okay. Next one is light energy. These are popular forms of energy. Light energy. Light is a form of energy. Green plants make their food in presence of sunlight. Similarly, when light energy falls on photographic plates, it causes a chemical change and hence images are recorded on the photographic film. The sun is the natural source of light and heat energy. Next one is electrical energy. Electrical energy. Electricity plays a vital role in modern society. It is used to operate fans, light bulbs, refrigerator, washing machine, etc. An electric cell is also a source of electrical energy. Next is chemical energy. So the energy stored in the matter is called chemical energy. Coal, petrol, kerosene, oil, wood, diesel, etc. all have chemical energy stored in them. When petrol is burnt in a car, the chemical energy stored in petrol is used to run the car. Okay. Sound energy. Sound energy. Sound is also a form of energy. A vibrating body possesses sound energy. When the sound produced by a vibrating body reaches our ear, what happens? It causes the ear membrane drum to vibrate, which makes hearing possible. Okay. Next one is magnetic energy. Magnetic energy. Magnet can attract iron filings or pins toward it and hence it possesses magnetic energy. Next one is nuclear energy. Next one is nuclear energy. The energy stored in the nucleus of an atom is called nuclear energy. The energy stored in the nuclei of atoms can be obtained by carrying out two types of nuclear reactions called nuclear fusion and nuclear fission. But here we will discuss about mechanical energy. And mechanical energy, it is nothing but simply the sum of kinetic energy and potential energy. So it includes what? Kinetic energy and potential energy. So what is kinetic energy? Kinetic energy. So the energy possessed by a body by virtue of its motion. So energy by virtue of its motion. Energy by virtue of its motion. Energy by virtue of its motion is called what? Kinetic energy. An object in motion has the ability to do work and hence possesses kinetic energy. Suppose there is a moving body, it is moving with 10 meter per second and hit, this is body A and this is body B. So A hit the body B, so after hitting, body will also acquire what? B. So it does work, A does work on B. Earlier velocity, initial velocity of B was what? Initial velocity of B was 0 and V is the velocity after hitting. Velocity after hitting by A. Okay, so A does work on B. So kinetic energy, of course, this body will be said to have what? Kinetic energy. Now examples of kinetic energy: wind possesses kinetic energy and can run windmills. Next one is the kinetic energy of flowing water is used to generate electricity. Next one is a bullet fired from a gun possesses kinetic energy and can penetrate a target. Next one is a moving car possesses kinetic energy. Okay. Now I am going to discuss expression. So expression for kinetic energy and so called work, it came from work energy theorem. Work energy theorem. So here, what is work energy theorem? Consider a mass m moving with uniform velocity v, initial velocity u. Let it now be displaced through a distance s, through a constant force F. Suppose a constant force, this is constant force. This is constant force acts on it. The work done on the object will cause a change in its velocity. So this force will cause change in its velocity. And now its velocity came what? V. Let A be the acceleration produced. Suppose acceleration of the body is A. So you all know V square is equal to U square plus twice AS, right? So from here you can get S is equal to V square minus U square upon 2A. This is equation first. And according to Newton's second law, the force applied on the body can be calculated from this formula. F is equal to m times A. This is equation number 2. And work done by force F, and this is nothing but simply what? Force into displacement. So W is F into S, and this is equal to F ma, and S is what? V square minus U square upon 2A. Okay, so what are you going to get? W is equal to half mv square minus U square. So this is nothing but simply half mv square minus half what? mu square, and this is known as change in kinetic energy. Okay, so the energy spent in doing this work of moving body from rest. Suppose I am giving you an example. U is equal to 0 and final velocity v final is v. So energy is spent in doing this work of moving a body from rest to attain a uniform velocity v is stored in the body in the form of kinetic energy. Therefore, work done, so we can write work done is equal to change in kinetic energy, and this is nothing but simply what? This is known as work done is equal to change in kinetic energy. This is known as what? Work energy theorem. Okay, and from here you got kinetic energy is equal to what? Half mv square. But this is the case when initial velocity was 0. Okay, now I'm going to discuss factors affecting kinetic energy. Factors affecting kinetic energy, and in abbreviation we have written K. So kinetic energy of a moving body depends on mass of the body and velocity of the body, because formula of kinetic energy is half mv square. So first, kinetic energy of a moving body is directly proportional to the mass of the kinetic energy is directly proportional to mass of the body. And if we plot a graph between kinetic energy versus mass, kinetic energy versus mass, so it will comes out what? A straight line. This is a straight line. Thus it includes that if mass of a moving body is doubled, keeping velocity constant, v is constant, the kinetic energy of the body, in this case, what effect will go? K will become 2k. Kinetic energy of the body also gets doubled. This is first point. Second point, if mass is halved, then velocity remains constant. In this case too, velocity is constant. Okay, the kinetic energy, what effects will go? Kinetic energy will becomes k upon 2. Okay, so this was factor 1. Now I am going to discuss factor 2. So factor 2 is kinetic energy of a body is directly proportional to a square of its velocity when mass of the body remains constant. Here m is constant. Earlier v was constant. Here mass is constant. So graph will comes out like this. If we have taken k on vertical axis and v velocity on horizontal axis, so graph will be like this. So what conclusion we can draw from it? If the velocity of a moving body is doubled, if v of a moving body is doubled, keeping mass constant, mass is equal to constant, so what effects will go over kinetic energy? In this case, k will become 4k. Why we are telling this? Because corresponding to v, kinetic energy was half mv square, and corresponding to 2v, k nu will be half m, and now v is 2v square, and this is equal to half into half mv, 4 times half mv square. Okay, So K will become 4K. Second conclusion, if the velocity of a moving body is halved, if V is halved, so kinetic energy, in this case 2 mass is constant, so kinetic energy of the moving body will become 1 upon 1/4 of the original value. Okay, and you can easily get it. One more expression I just want to put here for your uh, uh, for your information. Kinetic energy is what? Half mv square, isn't it? This is equation number first. Multiply and divide equation 1 by m. So what are you going to get? Kinetic energy is equal to half mv square multiplied by m divided by m. So kinetic energy is half m square v square upon m, and this is equal to half mv whole square upon m. And we all know that momentum is mass into velocity. This is what? Momentum. So kinetic energy is p square upon 2m. So this is one more expression for kinetic energy to solve numerical. Okay, now we are going to deal with potential energy. Potential energy. The energy possessed by a body by virtue of its position or its configuration, shape or size is called potential energy. An object may have the capacity of doing work as a result of its position in a gravitational field, an electric field or a magnetic field. Potential energy may be positive or negative, and potential energy is often referred as stored energy. Now I am going to give some examples. A heavy ball of a demolition machine has potential energy when it is held at an elevated position. Okay. A stone lying on the ground has no energy, so it cannot do any work. If this stone is lifted to the roof of a house, the work has been done in lifting this stone against the force of gravity. So if you are lifting it, so of course in this course gravity is acting vertically downward. So the work has been done in lifting this stone against the force of gravity. This works, this of course there is some driving force which is driving it up, and which is against the gravitational force. This work gets stored in the stone in the form of potential energy. So when it will reach certain height, acquire potential energy. For your information, I just want to tell all of you that potential energy is not the property of any particular body. Rather, potential energy is the property of this body plus earth combined system. This is system. So potential energy is the property of, is the joint property of system. Okay. Next example I would like to cite here. The water is stored at a height. Suppose this is water which is falling from a height. This is at height h, and this is water. So the water stored at height in a dam has potential energy it is allowed to fall, the falling water has the ability to rotate the turbine to generate electricity. If here will be turbine, so it will hit this turbine and it will start to rotate. So of course water which is here at a height h has capacity to do work and said to have potential energy. A stone resting on the edge of a cliff has potential energy due to its position in the earth's gravitational field. If it falls, the force of gravity, which is equal to the stone's weight, will act on it until it strikes the ground. The stone's potential energy is equal to the product of its weight and distance it can fall through. One more thing I would like to put here, elastic potential energy. Elastic potential energy. So the energy possessed by a body due to the change of its shape is called an elastic potential energy. The change in shape of the body can be brought by compressing, stretching or bending. For this change, some work has to be done. This work gets stored in the form of elastic potential energy. When this deformed body is released, it regains the original position and potential energy is given out in some other forms of energy. Now I am going to cite certain examples. When a bow is stressed, I am not very expert of making bow, but if this bow is stressed, stretch has been done, there is a change in configuration of its different parts, right? Work done on the bow during a stretching is stored in the bow as elastic potential energy. So it acquired, when we stressed it, this acquired what? Elastic potential energy. When the stressed bow is released, so when we will release, it will move fast to the right. The arrow moves forward with a greater velocity on account of potential energy of the stressed bow, which is imparted to the arrow. Okay, so these are basic things. Second, when a watch or clock, when a watch or clock is wound up, some work is done on the spring of the watch and it gets coiled more tightly. So this is the case, this is coil, and afterward what happens? Wound up, this is wound up, and normal shape. This one is normal shape of spring inside what? The watch. Okay, and this is wound up spring possesses energy. Possesses what? Energy. So when a watch or clock is wound up, some work is done on the spring of the watch and it gets coiled more tightly. This work gets stored up in the compressed spring in the form of elastic potential energy. As the spring unwinds, the potential energy is gradually converted into what? Kinetic energy, and the hands of the watch starts moving. So these are the mechanism behind running of any watch or clock. So second important thing, potential energy. Potential energy, this is potential energy of an object, of an object at a height, at a height or gravitational potential energy. Okay. So the gravitational potential energy of an object at a point above the ground is defined as the work done in raising it from the ground to that point against gravity. The gravitational the gravitational potential the gravitational potential energy of an object at a point above the ground is defined as the done in raising work done in raising it from the ground to that point against what? Gravity. So as far as expression for gravitational potential energy is concerned, expression for gravitational potential energy, suppose there is a block which was earlier on the ground, so this is its initial position, right? And we are lifting it through a height h. So of course this is final position. So what force is acting? Suppose during the course of its lifting, gravitational force was vertically downward. So during the course of its lifting, gravitational force was acting mg vertically downward. So of course a force must be operative on this body in vertically upward, almost equal to mg or little bit greater than mg. So approximately we treat it that force is equal to mg. So here F is equal to mg, where g is what? Acceleration due to gravity. Okay. So at the distance moved is in the direction, at the distance moved is in the direction of the applied force, work is said to be done. Okay. The object gains energy equal to the work done on it. Let the work done on the body against the gravity is W. So W is work done on the body against the gravity, against the gravity. So of course W is equal to force into displacement, right? And force, so F into H. So F is equal to mg and S is what? H. So mg into H. So this work mgh gets stored up in the form of potential energy. Thus gravitational potential energy is equal to work done on the body against gravity. So potential energy is equal to mgh. So this is the expression for potential energy. Now factors influencing influencing potential energy. First, potential energy. Potential energy. What was the expression for potential energy? mgh. So potential energy is directly proportional to mass when g and h is what? Constant. So if mass of the body is doubled, its potential energy, if mass of the body is doubled, so its potential energy will also become what? Twice. And if we plot a graph, here we have on vertical axis we have taken potential energy, and on horizontal axis we have taken, so this is your x-axis on which we have taken mass, and on y-axis we have taken what? Potential energy. So graph will come a straight line with non-zero slope. Second, potential energy of a body is directly proportional to height. Potential energy is directly proportional to what? Height to which the body is raised when mass and g, when m and g is constant. So rests are taken what? Constant. So of course potential energy, if we plot, here we have taken on x-axis height, and on y-axis we have taken what? Potential energy. So again this will comes out a straight line with non-zero slope. Okay, so these are basic things which we have to bear in our head. Now we will discuss some more thing: transformation of energy and law of conservation of energy. So transformation of energy, the change of one form of energy into another form of energy is known as what? Transformation of energy. Energy of wind. The sun's heat causes uneven heating of land and produces different air pressure at different places. These differences in air pressure produces wind having kinetic energy. Wind energy is used to run windmills. Okay, so we are discussing what? Transformation of what? Energy. So first was energy of wind. Energy of wind. Second is energy of food. So when we intake food, the plants use the sun's energy to prepare food by the process of photosynthesis, right? This energy gets stored in the food in the form of chemical energy. Humans and animals eat these plants as food. This plant food supplies energy to human and animals. Muscular energy is used by humans and animals to do work. It means the muscular energy of living being is derived from sun's energy. So different human activities consume energy at different rates. For example, when we run fast, we consume more energy than we walk slowly. The energy consumption of a body of 40 kg weight for some activities are given below. Sleeping. In case of if you are sleeping, this is taken for 40 kg person. Okay. Sleeping consumes 3.2 kilojoule per minute. Walking. Energy consumed in this is 10.9 kilojoule per minute. Okay. Running fast. Running fast. It consumes 22.7 kilojoule per minute. Swimming. It is 25.6. Its consumption is 25.6 kilojoule per minute. Okay. Now, next thing is energy of fossil fuel. I am continuing it. Energy of fossil fuels. Fossil fuels. So the dead plants and animals buried under the earth millions of years ago have been converted into fossil fuels like coal, petroleum, oil, and natural gas. The energy of fossil fuels can be used to produce thermal energy, electrical energy, and mechanical energy. And next one is energy of flowing water. Energy of flowing water. So the sun's heat energy causes water to evaporate from lake, rivers, and oceans. The water vapors rise in the air to form clouds. When this water falls back to the earth in the form of rain, some amount of it gets stored in the high dams. When this water is allowed to fall from high dam, its potential energy is converted into kinetic energy, which can be used to turn turbine in the dams to generate what? Electricity. One more of important thing is an extremely important law of conservation of energy. Law of conservation of energy. So Einstein stated that energy can neither be created nor be destroyed. It states that energy can neither be created nor be what? Destroyed. But transformation take place. Transformation allowed. Transformation may happens. So these are the statement of law of conservation of energy. So now I am going to discuss verification. Verification of law of conservation of what? Energy. So consider a pendulum which is vibrating in this mode. This is position A and this is position B. So if it has velocity v, so of course at A it has only kinetic energy. Okay. At B it reached certain height, so at this position it has only potential energy. So this kinetic energy converted into potential energy. But in the mid, see, some kinetic energy plus some potential energy. But overall, K plus U will remain what? Conserved. So only what is happening if K plus U is conserved. So when K will decrease is equal to conserve. So U will have to raise, and if K will raise, then U will have to be diminish, will have to be decreased to remain conserve K plus U. So these are the features of conservation of energy in case of Bob. Okay, so we have discussed today lots of things, right? So now I am going to wind it up. Thank you so much to all of you for showing your great patience.